Hello and welcome to this IB Maths Intense session, part of our topic number 3, geometry and trigonometry. This is all about volume and surface area of 3D solids, and this is something that has appeared on the specification for the new IB Maths spec, and you can see there SL 3.1 we're being asked to be able to work with volume and surface area of three-dimensional solids, right pyramids, right cone, spheres, hemispheres, and combinations of these solids. It sounds really quite a scary topic. And prerequisite knowledge for this is the stuff that we did earlier on the earlier videos in this topic to do with right-angled triangles and use of Pythagoras in 3 dimensions, but also some prerequisite knowledge. We need to try and remember the work we did in our earlier maths career on similarity of shapes, especially when that similarity or a scale factor is applied in 1, 2 or 3 dimensions. And I'll give you an example to show you what I mean in a second. Now thankfully we're given all the formulae we need. They're all on the formula sheet. There they are: volume of right pyramid, right cone, area of a curved surface of a cone, volume of a sphere, and surface area of a sphere. So you don't need to learn any of these formulae, but you certainly need to be able to use them. And you know what the IB are like. They're not going to ask you just to work out the volume or area by just using the formula. There's always going to be something that requires you to do a little bit more with the formula in order to be able to use it. So let me give you a couple of examples, but just to say, it's impossible in a short video like this to give you every possibility that they might ask you, but these give you some examples or ideas of the kind of working or thinking that you're going to have to apply for this topic. So in this first question, nice straightforward one, we're just being asked to find the volume and surface area of a pyramid. So the routine here is obviously just to take a look at what we're being given. And this is a pyramid where the base is a square, 15 by 15, and the height of the pyramid is 15 centimetres. So if I look at the formula sheet, I can see I've got the formula for the volume of a right pyramid right there. The volume equals 1/3 AH, where A is the area of the base and H is the height. So just looking at this triangle, that's quite nice and easy. The area of the base is equal to 15 squared, because it's a square there at the bottom, which is 225. And the height, we're also given that, it's also 15. So that's very easy, isn't it? The volume is going to be 225 times 15, which gives us a nice answer of 1,125 centimetres cubed. Just to remember, because this is very likely to come and haunt you, that 1,000 centimetres cubed is equal to 1 litre when we're talking about capacity. So you could have given your answer there as 1.125 litres, because that's another equivalent measure of volume. So there's the first part, that's nice and easy. But the surface area question is a little bit more difficult. So let's have a look. You're not given a formula for the surface area. You're expected to be able to work out that you need to find the area of each of the 5 sides of that pyramid shape. So the base. So the area of the base is nice and straightforward. That's just 15 squared, which is 225. But we now need to find the area of each of those triangles, those right-angled triangles, those triangles, which aren't right-angled triangles, that make up the 4 sides. So let's have a look at how we find the area of one of the triangular sides. Well, we're going to need to use the work we did on right-angled triangles to find some proportions, because we know the area of a triangle is half base times height, and I've got the base, it's 15. But I need the height, and to find the height, if you can see, I'm just going to construct a right-angled triangle there, and you can see that that right-angled triangle has got dimensions of 15 as the height, and then half of the width of that triangle, 7.5. So my perpendicular height for the side is going to be, using Pythagoras, is going to be 15 squared plus 7.5 squared, all square rooted, and that will give me a height of 15 root 5 over 2, just using my calculator. So now I've got a triangular side there with a base of 15 and a perpendicular height of 15 root 5 over 2. So area is half base times height, which is a half of 15 times 15 root 5 over 2. And that will give me the area of one of those sides is equal to 125.78 centimetres squared to 2 decimal places. But of course there are 4 of those, so the total surface area is going to be the area of the base, which is 225, plus 4 lots of the sides, 4 lots of 125.78. And if I calculate that, that will give me a total of 728.115 centimetres squared. Be careful with your units of measurement. This is area, so it's centimetres squared, not centimetres cubed, which we used when we were working out volume. So what we've done there, we've just applied the knowledge that we learnt in the earlier video about constructing right-angled triangles in a 3-dimensional shape to find missing lengths, or we could have found angles, I guess, as well. Let's have a look at a slightly more complicated question. This one is about a cone, and we're told that a cone has a base with a circumference of 50 centimetres and has a capacity of 5.2 litres. Now, the first thing I'm going to do there is just highlight what I've been given. Circumference is 50, capacity is 5.2. Now, 5.2 litres, I'm just going to write that down here, is equal to 5,200 centimetres cubed. And I want to work in centimetres cubed because the circumference is in centimetres. So I'm just making my units of measurement the same to start with. Now, what I also need here is my formula for the volume, because if I've got the volume, I can work backwards to find the height. And sure enough, down here, the volume of a cone is there, 1/3 pi r squared h. So volume equals 1/3 pi r squared h. Just write that down there so that I've got it. I know the circumference is 50, so I could work backwards from that to find r. So if circumference, we know, is equal to 2 pi r, so if c equals 50, then 50 equals 2 pi r. That means my radius must be 50 over 2 pi, which is 25 over pi. So we're on our way. We've got the radius. What we need to find is the height. So let's work backwards from our formula for volume. Volume is 5,200. That equals 1/3 pi times the radius squared, that's 25 over pi, all squared, times the height. I could just tidy that up a little bit so that I'm not carrying around so many terms. 5,200 equals 625 over 3 pi h. Rearranging that, my height is 5,200 over 625 over 3 pi. Working that out on the calculator then, I get my height is equal to 624 over 25 pi, which is an exact answer. If they ask for different units of measurement, maybe they ask it to 2 decimal places, that's approximately equal to 78.41 centimetres. Brilliant. So I managed to do that. Now the second question is a little bit more difficult. It says, find the capacity of a similar cone. A similar cone, that means all of the sides are in the same proportion. So find the capacity of a similar cone which has a radius of 10 centimetres. So the first thing we need to know is what's the relationship between the height and the radius. And then we can apply that same scale factor. Well, in the first question, we worked out that the radius was equal to 25 over pi, if you remember. And our height in that first question was equal to 624 over 25 pi. Notice I'm leaving everything in terms of pi so that I get more exact measurements. So the relationship between height and radius, if I divide height by radius, 624 over 25 pi divided by 25 over pi gives me a scale factor of 9.8538. Okay, that's just dividing the measure for height by the measure for radius. And that tells me that height is 9.8538 times bigger than the radius. So if radius was 10, my height would have to be 9.8538 times 10, which is 98.538. Scale factor stays the same when I have a similar cone. If my radius is 10, my height will continue to be 9.8538 times bigger than the radius, so it must be 98.538. And then I can just go back to my formula for volume. Volume is 1/3 pi r squared h. And putting the numbers in here, we've got those out. That would be equal to 1/3 pi. R is 10 squared, so times 10 squared, and then times 98.538, which is my height. And that will give me an answer of approximately 10,319 centimetres cubed. But of course, in the question, I was given my units of measurement for capacity in litres. So dividing by 1,000, that's approximately 10.32 litres. Those little bits and pieces, like your units of measurement, just be careful with those on these kind of questions, because the examiner will be happy to deduct a mark if you're not using the correct units of measurement in that way. So, again, not too difficult. Just remember those aspects of similarity of shapes. On that same topic here, here's a question where we're not actually given any numbers at all. We're asked, by what factor is the volume of a sphere increased if the surface area is doubled? Now that's quite tricky, isn't it? Volume and surface area of a sphere. Well, we've got the formulae down here. Let's just put that in a highlighter pen so you see it. Volume and surface area of a sphere. The question is, what happens if we double the surface area to the volume? Now, there are two different ways we could do this. I'm going to show you the long way round first, and then I'll show you a much quicker way which uses the properties of scale factors. In the first instance, if you're given no numbers, let's just make some up. So let's just assume that the surface area maybe is 100. And that was calculated by 4 pi r squared, which is my formula down at the bottom for the surface area of a sphere. That tells me that r squared must have been 25 over pi. So my radius was 5 over root pi. And then if I doubled it, well, let's go on and say if the radius was 5 over root pi, let's work out what the volume would have been of that sphere. The volume would have been, using the formula for the volume, it would have been 4 over 3 pi times the radius cubed. So that's 5 over root pi cubed. There's my formula down there, 4 over 3 pi r cubed. And I'll leave it like that just now, because leaving it in terms of pi gives me an opportunity to simplify later. But just for the note, that's approximately equal to 94.03. Now let's double everything. let's double the surface area. So imagine the surface area was now 200, and that was equal to 4 pi r squared again. That means this time r squared must have been equal to 50 over pi. And that means r must have been equal to square root of 50, which is 5 root 2 over pi. Just doing the same thing, what I've done is I've made imaginary numbers and just doubled the surface area from 100 to 200 to see what happened to the radius. And now if I go and do the same thing with the volume would have been 4 over 3 pi. This time, 5 root 2 over pi cubed. And that, if I wanted to do that, is approximately equal to 265.96. So by what factor? The scale factor, if I call this one B and this one A, the scale factor must be equal to B over A. But it's much better to use the original measures that have got pi in them than the ones that I've just rounded at the end. And if I do so, I get a precise answer. So 4 over 3 pi times 5 root 2 over pi all cubed divided by 4 over 3 pi times 5 over root pi cubed will give me the precise answer of 2 root 2, which is approximately equal to 2.83. But it's much better if you can give the exact answer of 2 root 2. Now there's something about that number there that looks very, very tidy. And it tells me that maybe there was a better way and a quicker way of coming up with that answer. So let's have a look at another way that I could have done that would have saved me a lot of time. So let's have a look at what happens with 1 dimension, 2 dimension, and 3 dimensions when we increase or decrease things by a scale factor. Now we know if we have, in this case with a sphere, the 1 dimension that we're working with is the radius. The 2 dimensions we're talking about here are the surface area. And the 3 dimensions we're talking about the volume of the sphere. Now in general, let's imagine I doubled everything. If I double the radius, the surface area wouldn't be doubled. It would be increased by a scale factor of 2 squared, because I'm working in two dimensions. So the impact of the radius being doubled is now working in 2 dimensions. So it must be an increase of 2 squared. And the volume, because we're working in 3 dimensions, will be increased by a scale factor of 2 cubed. And in general, I can say if the scale factor is A, for the radius, the 1 dimension, the surface area will increase by a scale factor of A squared, and the volume will increase by a scale factor of A cubed. So what do we know? Well, we know that the surface area was increased by a scale factor of 2. It was doubled. That means my scale factor for the radius of A must be the square root of 2, because if A squared is equal to 2, A must be equal to root 2. So an A cubed must be root 2 all cubed, which is actually 2 root 2. And miraculously, that is the answer that we got working things out a long way. And remember that with the increasing things by a scale factor, what that does in 2 dimensions and then 3 dimensions. So for example, if I halve the radius, then my surface area would be a quarter of the surface area of the original, and the volume would be 1/8, a half squared, and a half cubed. All good stuff. Hopefully that gives you a flavour of the kind of things you're being asked to do. I can't cover absolutely every possible question for every possible shape. There's just too much to cover in a short video. But just remember these tips. Remember that similar shapes share all their sides in the same proportion. And so if you're told that a shape is similar and the height has been doubled, then it shares particular relationship with one of the other sides, then the ratio of those sides will stay the same as you increase it. Remember the thing I just told you there about scale factors, that if you've increased something by a scale factor of a in one dimension, then in 2 dimensions things will be increased by a scale factor of a squared, and similarly by a cubed in 3 dimensions. You're being tested here in applying 3D Pythagoras to find missing lengths by the use of right-angled triangles. So be good at sketching things and being able to find the appropriate right-angled triangles to find those missing lengths. And as with all IB Maths problems, break the problem down into smaller bits, write down what you know as you're going along, tell the examiner the story that you're following, and of course, keep your formula sheet close by, because you're going to need it for these questions, because it's unlikely that you'll be able to remember all the formulae. I certainly don't remember them, I just use the formulae sheet. Anyway, there we go. That's volume and surface area of 3D solids in a short video. I hope that was helpful. Thank you for watching. Don't forget to like this video, and of course subscribe to my YouTube channel, IB Maths Intense. Tell your friends I'm here. Send me an email, ibmathsintense@gmail.com, if there's anything you want me to cover. And of course, keep enjoying your maths and stay healthy. Take care.